So I want to finish up our discussion of end-to-end packet forwarding through this network by focusing a little bit more on what the routers themselves are doing. But before we start with that, I want to just take a closer look at what is inside an IP packet. And so, of course, we have our Ethernet frame, which we've been looking at before, and the IP packet sits inside the payload of this frame. So this payload is going to encompass our entire IP packet, which is going to include the IP header as well as whatever payload is inside the IP header. And so anytime we have an IP packet, the ether type is going to be 0800. And remember, there's either the ether type or the protocol field if this is PPP. So we're looking at Ethernet, but IP can go over PPP as well, or any other layer 2 data link framing mechanism. And then that framing mechanism is going to either have an ether type or a protocol of some sort that's going to tell you what the payload is. And in those cases, the 0800 indicates that it's IP. Then within the IP header, there's actually a protocol that tells you what is inside the IP packet. So when we were doing the ping before, we were using the Internet Control Message Protocol, or ICMP. And the protocol for that is actually 1. So you see we have this thing where we have this Ethernet frame that uses the ether type to tell you what's inside it is IP, and then an IP header that uses this protocol field to tell you what's inside the IP packet is ICMP. And so this is a pattern that you're going to see a lot in networking, which is called encapsulation, where you have one protocol encapsulating another protocol, which maybe encapsulates another protocol, and so on. And hopefully as we go through this, you'll see that each of these protocols has a specific purpose. But getting back to the IP header, I just want to walk through these different fields. The IP header starts off with a version, and what we're talking about is IP version 4, which uses 32-bit addresses that we've been looking at. There's also IP version 6, which is starting to gain some popularity on the internet, although it's still a very, very small percentage. The next is the internet header length, and this is the length of the IP header, because down at the bottom there's some options that you can have, and the length of these options is variable. But in practice, you will probably never see, or almost never see, an IP packet with any kind of options in the header. It's very rare to see that these days. They were sort of added to the protocol very early on, but it turned out it wasn't very useful. So you almost never see that. And so the header length is always, or almost always, going to be 5. And what that means is there's 5 words, 32-bit words. And so this, you can think of this as, each of these rows is 32 bits. And so this 5 means that there are 5 of these 32-bit rows here. And if there were options, this would be 6 or 7 or 8 or so forth. And then we have the type of service field, which is an 8-bit number that indicates how the routers in the network should prioritize this particular packet. And oftentimes it's not used, but one case where it is used is for routing protocol traffic, which is the routers communicating between each other to exchange routing information. And so the routing information is of course very important to the network functioning properly. So the routers want to prioritize that traffic, and so they'll set the type of service field to a different value to indicate that. And that's the most common usage. It can also be used to provide different levels of service in larger networks or networks that have customers that are paying more for better service, that sort of thing. It could be used. The next couple fields, the total length, the identification, the flags, and the fragment offset, these are all used in IP fragmentation, which I'm not going to talk about just yet. I may make another video where I go into that in a little bit more detail. The time to live field is just an 8-bit number that is set by the sender, and then each router that the packet goes through, it's decremented by 1. And then if the time to live ever gets to 0, then the router will just discard the packet. And the reason for that is to try to prevent loops. So if we look back up here, you could imagine if a packet comes in here and Denver thinks that to get to wherever this packet is destined, it should be sent to New York, and New York thinks that it should be sent to Atlanta, and then Atlanta thinks it should be sent to Denver, then Denver's going to send it back to New York, and so on, and this packet is just going to get caught in a loop. And so to prevent this from just like looping indefinitely, the time to live field is decremented at each hop. And eventually the time to live field will get to 0, and one of these routers will just drop the packet. And usually this loop like this might indicate something is gone wrong, but it can happen occasionally when the routing protocols between the routers are in a transitory state. And so you might have loops in a network, and that might be normal, but it usually doesn't last for very long at all. But just to handle the case where they do come up, we have this time to live field that sort of takes over and will drop a packet if all else fails. And then finally, we have this header checksum, which works sort of like the frame check sequence in either Ethernet. Remember the frame check sequence either in the Ethernet frame or in the PPP frame. And it's just a checksum of the values in the IP header. And so it's actually not that useful because we already have this frame check sequence on the Ethernet frame or on the PPP frame or some other data link level framing mechanism is usually going to have a frame check. So this header checksum is a bit redundant, but it was part of the protocol, and so it exists, and that's what it does. And then finally, there's the source address and destination address, which are just the source and destination IP addresses of where this packet is coming from and where it's going to. And it's the destination address is the one that the routers are looking at to figure out how to forward it. And then right after the IP header, we have whatever data is in the IP packet itself. And in future videos, we'll explore some different things that we might see inside an IP packet. But what we've looked at so far is just this ICMP message, which is the ping message. And the way that we know that we have an ICMP message is that this protocol field is going to be set to 1. If this protocol field were set to something different, then we would have some different data here. And again, in future videos, we'll look at what some of those things could be. But for now, let's go back up and look at our network and look at exactly what these routers are doing as we go through. So remember, we have a packet that we're sending from this 192.168.9.2 address over here, and the destination is the 20.2 address over here. So this is the destination address in our packet that we're sending, and it's the destination address that each of these routers is looking at. So all of the routing decisions are based just on the destination address. And so in the previous videos, we saw how 192.168.9.2 is going to forward its packet to the San Francisco router. But now let's take a look at what's actually going on inside that San Francisco router. So if we look inside the San Francisco router, it's going to have a routing table. And this is a snapshot of the actual routing table that's in there, so we can take a look at what's going on. And so again, this packet is coming in with a destination of 192.168.20.2. And so San Francisco is going to look in its routing table and try to find an address that matches. And so we have, or a prefix that matches actually. And so the prefix it finds is 192.168.20.0/24. And so the /24 means we're only comparing the first 24 bits, which really means just the 192.168.20 part. And so 192.168.20 matches the first 24 bits of 192.168.20.2. And so it's going to choose this route right here. And there's a couple things that we can see here. So the most important part here is the next hop. And so that's what's being shown here is it says to get to 192.168.20/24, that prefix, go to 10.0.15.2, which is right here, via EM2. So it's interface 2. So it's saying take that packet and send it out this direction towards Denver to this 10.0.15.2 address. So now that the packet has arrived at Denver, Denver is going to look at it and it's going to do the same thing. It's going to look in its routing table for the 192 for a matching address or for a matching prefix. And so the matching prefix it's going to find is the same one, 192.168.20.0/24. So the first 24 bits of this again matches that destination we're looking for over here. And this time it says to send it out or to send it to 10.0.21.2 via EM3. And so interface 3 is right here. And then the 10.0.21.2 next hop is New York. And so it's going to send it out this interface here. And so if we look at New York's routing table, we see that 192.168.20/24 prefix. And now it says via EM3, which is interface 3 over here. And it doesn't give us a next hop, and it says it's directly connected. So what this says is that this address is directly connected to this interface. It's on this same Ethernet network. And so that tells the router that it needs to go ahead and do an ARP for 192.168.20.2, and it's going to do that same ARP process that we saw before, and then deliver that Ethernet frame. Once computer B gets that packet, if it wants to respond, then it's going to send its response back to 192.168.9.2 over here. And so we can actually do the same thing in reverse. So B is going to be configured with 192.168.20.1 as its default gateway, and so we'll ARP for that, although it will probably already know the MAC address because it's already received traffic from here. But if it doesn't, it'll ARP for that, and then it'll send its frame to New York with a destination of 9.2. And then if we look in New York's routing table, it has a route for 192.168.9/24, which matches the 192.168.9.2. And something that I didn't point out before, but which is kind of interesting, is you can see this metric 3, and that, in this particular case, tells us the distance to this, which is 3 hops. So it's 1 hop, 2 hops, 3 hops, which is just kind of an interesting little side note there. But in any event, this says to go to 10.0.21.1 via EM1. And so here's EM1, and we go to 10.0.21.1. So we're taking the same path back, which it doesn't have to do. It could take a different path back, but in this case, the way these routes are, it happens to be taking the same path back. And then same thing, if we look in Denver, we're looking for that 192.168.9/24 route, which matches our destination now of 192.168.9.2. And this says to send it to 10.0.15.1, which is right here, via EM1, which is interface 1 here. And you'll see here it says metric 2, so now it's only 2 hops away, so we're getting closer. And then finally, when we get to San Francisco, we look at our routing table again, and we see that 192.168.9/24 is directly connected via EM3, and so we can go ahead and deliver that packet finally on this Ethernet over here. And something I want to point out is that actually if you look through this entire routing table, you'll see there's a bunch of routes to all of these other little networks along here. So from this host here, if we tried to send traffic to any of these routers interfaces, we should have a route that takes us there. And I would encourage you actually to go through this video and kind of pause it at the different spots to look at the routing tables in each of these routers and see exactly what this routing table looks like. There's a couple interesting things. Actually, one thing that I would point out, for example, is at Denver, if we're at Denver here, the route to 10.0.8/30, which would encompass 10.0.8.1 and 10.0.8.2, we actually have 2 different ways to get there. This one says you can go to 10.0.16.2, which is over here, via EM2, out this interface, or you can go to 10.0.21.2 via EM3, which is out this interface. And both of those have a metric of 2. So what it's saying is that to get over here to this network right here, we can either go this way or we can go this way. And either way, it's 2 hops. Either we're going through New York or we're going through Atlanta. Either way, it's the same distance. And so I think it's just interesting to see that there are 2 ways to get there. And in this particular instance, the router has chosen to prefer this route. But when we talk more about routing protocols, we'll see how you can influence that and how those decisions are made in more detail. But I would encourage you to go back through this video and take a closer look at these routing tables to kind of see how this works and to kind of convince yourself that all of these routes that are in these routing tables make sense.